This is the 6.3 video for polar coordinates for Math 127 at Damonte Ranch High School. And so we're going to be looking at some really interesting shapes over the next couple sections. You might see, like, there's a circle, which you're familiar with, but this other shape that you probably don't have a name for yet, which is fine. We're going to learn some names and a different way of kind of naming coordinates, which leads to some interesting equations and different ways to represent shapes that we don't maybe have any exploration for so far. So to start off, we're going to talk about a different type of coordinates called polar coordinates. So what are they? They're a way to name a point based on it's different from the origin. And so what we're going to say is that we could have like an XY axis. I'll try to graph it. That we're looking at. And really, this is kind of our starting point. This is very related, by the way, to the unit circle. And when we talk about a point, what we want to do is we want to be able to name how far is it from the origin. We'll call that R for a radius R. We also want to measure where is the position of that angle with respect to what we'll call the polar axis, or like your x-axis. And we're going to always measure this counterclockwise if we're using positive angles, which is probably the most common way. And so what we're going to do is, if I'm trying to name something, I want to be able to say how far away is it from the origin as a linear measurement for the radius. That would be the first coordinate right here in the R position. So we're still going to have two coordinates, but instead of x, y, we're going to use r theta. And then how far is the position in terms of an angle usually measured in radians? We're going to use radians. And that would be measured from the positive side of the x-axis or the polar axis. Polar coordinates, polar axis. So they're going to be written in this form. Now we could write a negative angle, and if we ever use a negative angle for theta, we're just going around counterclockwise instead of clockwise. So you'll see that sometimes. Rectangular coordinates are the coordinates that you're used to, the x, y coordinate planes, where x tells you how far you're moving from the origin horizontally, y tells you how far vertically. Again, those would pair together to give you a point. So just like the polar coordinates pair together to give you a point as well. Just a different measuring system. There's some things that we'll need to know if we're trying to convert. We'll come back to this a little bit more later. And we'll derive this so you can see where it comes from. But x is r times the cosine of theta. Y is r times the sine of theta. And again, this is going to be very related to a unit circle. We'll come back to that, to some things we already know. Also, something else, if we're converting, maybe we're starting with rectangular, we're trying to move to coordinates, polar coordinates. We'll come back to this, but r can be found by doing the square root of x squared plus y squared. That should look a lot familiar. This is essentially the same thing as the magnitude, which hopefully that makes sense. When we're dealing with vectors, we're just changing what we're calling it here. Slightly different language, we're calling it the radius, or r. To find tangent, similar to what we would do with vectors, theta could be found by taking the inverse tangent of y over x. We will derive that as well. All right, but let's just start with plotting them. So let's say we're given these three different sets of polar coordinates. Now, most of the time, polar coordinates are done in radians, but I am going to show you what it would look like if it's in degrees, just for your curiosity. So here's a typical polar graph. Polar graphs have can look a variety of different ways, but there's a couple things that I want you to notice. This would be your 0 degrees or your 0 radians. This would be the 90 degrees or the pi over 2 for radians, just like when we're dealing with the unit circle. And 180 degrees or pi radians, 270 degrees or 3 pi over 2 radians. And this could also be called 2 pi as well if we're in radians. So this particular one, you'll notice the notches on the x-axis and the y-axis here. And those notches can correspond to lengths of a radius. So we're drawing these in circles because we're going to find that this is very related to circular shapes. In fact, polar coordinates will have kind of a circular shape to them, not always perfectly symmetrical. But you'll see the smooth curved shapes on these polar shapes that we'll look at particularly next lesson. And so this one goes out 1, 2, 3, 4, 5, like a radius of 5 units long. And then we could change how we kind of divide up this polar coordinate system here. And so what this one has done is we've taken this first quadrant of 90 degrees and split it up into 3 sections of equal parts. So these are each like a 30-degree section, or we could think of it as like a pi over 6. This would then be 2 pi over 6, which reduces us to pi over 3. And again, radians is most common, but we could also view these in degrees. So what's not shown is where's the 45-degree angle. I mean, it's in here. It's just not drawn in as a radius, but that would be right here. And not everyone sets up their graphs for polar graphs the same way in terms of how they divide up and represent the different angles on the picture. But that's kind of how the one that I chose to use, that's how this one works. Okay, so we kind of divvied up with the pi over 6s as kind of our unit of measurement going around for those radian angles. All right, so if I want to do 3, I'm going to go 3 units in the direction of the angle of 315 degrees. So where is 315 degrees? Well, remember, we're measuring it from here, and we're going around 315 degrees. So there's 180, 270. So 315 would be 45 degrees past 270. So we're really looking along this kind of angle measurement, but I'm only going to go out 3 units along this. So I'll go out 1, 2, 3 units. So right here is where we would have 315 degrees, but I'm going to go out 3 units to name point A. So point A is this point right here. Point B, I'm going to go out -2 units in the direction of pi. Well, that's really interesting because r is negative. So what does that mean? Well, the direction of pi is along this. This is the direction of pi, but I want to go -2 units. Well, if it was +2 units, I would have landed here, go Broncos. However, that's not what they said. They said -2 units. So if this is the direction of pi, and we want to go -2 units, what you're actually going to do is you're going to stay along that straight line, but go back the opposite direction 2 units. So you're going to actually go back this way. So point B is right here. Now that has a different name. It doesn't just have to be called -2 pi. We could also call this 2, 0. Or 2 pi, depending if I want to go around the circle, or 2, 4 pi, etc. So there's a lot of equivalent names for each of these points. You could actually have an infinite number of coordinates for any of these points that are just different representations of the same point, depending if you're using a positive angle, a negative angle, a positive radius, a negative radius, or how many times you might go around this circle. Point C, I'm going to do -1 for my radius. So again, I'm going to be going in the opposite direction, in the direction of negative pi over 2. Well, positive pi over 2 would be this direction. Negative pi over 2, just like with the unit circle, would be this direction. So I'm along this. This is the angle direction that I'm going in, but because I'm going -1 units, I'm actually going to go back up this way. So point C is here. And so again, there are equivalent ways to name point C. I could also call this 1 unit in the direction of pi over 2. Would for most people be an easier way to represent this. Usually the more positive angle measurements and positive radii that you use, the easier it is for most people to understand where that point would be at. So those are some examples of how to plot those points. All right, now this one is going to use that idea again that every one of these points has an infinite number of polar coordinates. So different ways to represent this. So we're going to take this point and we're going to represent this 3 different ways. Sometimes r will be positive, sometimes negative, and we're going to change the range of values for which our angle can be measured with. So let's just start by putting this point where it actually goes. So we're going to go 5 units in the direction of pi over 4. So pi over 4, again, is halfway in between pi over 3 and the pi over 6. So this is pi over 6 and pi over 3. So here's pi over 4. So this is kind of the radius that we're working along, or the direction, the position that we're working on, and I want to go out 5 units from the origin. 1, 2, 3, 4, 5. So here's the point. So that's the point that I want to repeatedly represent. But I want r to stay positive, but I don't want my angle measure to be pi over 4. I want it to be between 2 pi and 4 pi. Well, the easiest way to do that is just to loop around this circle one more time. So I'm just going to add another 2 pi to this. Well, 2 pi with a denominator of 4 could be written as 8 pi over 4. So I could then say my angle measurement is now 9 pi over 4. I'm still going to go out 5 units in that direction. If r is negative, then what I want to think about happening is I'm going along the position the exact opposite direction. So what is the pi over 4 angle that's past pi? This is 5 pi over 4. And so I want r to be negative, so I'm really going to be looking along this position, but then since I'm negative, it would pop me backwards onto this position. And I want my angle to be in between 0 and 2 pi, which 5 pi over 4 is. So I'm going to call this negative 5 and 5 pi over 4. So I'm going to go to the angle position of 5 pi over 4. But then since I'm going with a negative radius, I'm going to go back exactly 5 units the opposite direction, which would land me at 5 pi over 4. I want r to be positive again this time, so I'll be using positive 5 for r. And I want my angle theta to be measured with a negative angle in between negative 2 pi and 0. So for this particular one, I want to be able to move around clockwise to get to this angle. The easiest way to do that would to take my pi over 4, which is where I want to land at, and remove 2 pi. Or remove, if I make that a denominator 4, remove 8 pi over 4. And I'll end up with negative 7 pi over 4. Just a different way to name that angle if I'm going clockwise instead of counterclockwise. For this next section, we're going to be converting. And we're going to be converting things from rectangular coordinates, from polar into rectangular. So we had a little bit of information up here, and I told you I would kind of help you understand that. We're going from polar to rectangular. These are the formulas that we're going to be using. You might wonder why that's so. Well, let's just go back to maybe something we're familiar with, which is the unit circle. And let's say I maybe am dealing with this point right here, which is poorly drawn. But let's pretend that this point is at pi over 6. Well, pi over 6 is root 3 over 2, 1/2 on the unit circle. And where that comes from is that the unit circle has a unit measurement of 1. And pi over 6 comes from a 30-degree angle. 30-degree angles are at the ratio of 1 root 3 and 2. But we've scaled this down. Instead of the radius being 2, the radius is 1. And so we could then say that horizontally, each of these measurements are then scaled down by divided by 2. And that's how we get the cosine, which is our x-coordinate, is cosine, and the y-coordinate is sine. So we're probably familiar with the idea that cosine is x and sine is y when we're looking at the unit circle. But what if our circle is not a unit circle? What if our circle is an enlarged version of the unit circle? So maybe now instead of the radius being 1, I'm not going to be able to draw this very well to scale because of the amount of room. But let's say we're looking at the same positioning of this angle, but now my radius is 10. Well, this is still the same triangle. This is still the same triangle. It's just an enlarged version of this triangle. So each of these sides is now 10 units larger than it was before. So, but multiplied by a scale factor of 10. So the coordinates of this point now would be 5 root 3 and 5. Well, how does that compare to the cosine and the sine? Well, basically that was the cosine multiplied by the length of this hypotenuse, which we're naming r. And the sine multiplied by r. So this x-coordinate was r times the cosine of theta, and the y-coordinate is r times the sine of theta. So that's where this formula comes from. It comes from taking our unit circle and just creating a dilation of it and multiplying it by the scale factor, and the scale factor is r. So that's what's happening on these. So if I'm looking at questions 5 and 6, I want to figure out and convert this to x comma y. right now, this is r comma theta. And it might be helpful to draw just a little sketch. So what we've got is we've got a situation where we're going in the direction of pi, 3 units. So we're right here. Now, some of these, you're going to be like, I already know what that is. Like, we should already understand that that is negative 3, 0, just from looking at the picture of this. But we could use the formula. X is r times the cosine of theta. In this case, theta is pi. So this is 3 times the cosine of pi and 3 times the sine of pi, since the y-coordinate is r times the sine of theta. Well, the cosine of, I don't know why I wrote theta. Let's write pi. That might be more informative. Since the cosine of pi is negative 1, there we go. And since the sine of pi is 0, we'll get to our answer that we could have found without actually using the formula, just by thinking. Let's take a look at this next one. So r is negative 10, theta is pi over 6. So if I'm trying to convert this to x comma y, basically what I want to do is I want x cosine of theta and y cosine of theta. Oh, sorry, y sine of theta. Oh my goodness, I should pay attention. R cosine of theta and r sine of theta. There we go. That'll give us our x and our y. You can draw a picture if you think that that would be helpful. In the direction of pi over 6, which is right here, we're going negative 10 units, which really means we're going over here. We're going 10 units, so this would be a length of 10 in the direction of 5 pi over 6. So we want to figure out where exactly is this point located. Well, we could think of this as negative 10 times the cosine of pi over 6 and negative 10 times the sine of pi over 6. So I'll end up with negative 10 times root 3 over 2 and negative 10 times 1/2. So I should end up with negative 5 root 3 and negative 5. I mean, you can verify. Does that seem like that would be in the correct quadrant, for example? And the answer is yes, this would be in the third quadrant with both of those being negative. And if you think about what you know about 30, 60, 90 triangles, that does make sense. That does match the patterns for a 30, 60, 90 triangle. Oh, and it says verify this by plotting both of them. So here we go. Negative 10 pi over 6 would be right here. This would be negative 10 units in the direction of pi over 6, or 10 units in the direction of 7 pi over 6, if you'd rather. And if I plot negative 5 root 3, negative 5, let me just get a sense of where that would be. I'm going to open up a calculator real fast to convert negative 5 root 3 to a decimal. Sorry, as we wait. Let me get out of the mode I'm in. Okay, so negative 5 square root of 3 is around negative 8.7. So I'm going to go what I think is negative 8.7. Here's around negative 8.7 and then negative 5. And I just want to verify that those points seem to be in the same spot. I tried to make those graphs around the same scale so that we could compare, but that looks pretty good. All right, for these next ones, this time I'm given rectangular coordinates. So these are currently x and y values, and I want to convert this to r values and theta values, r and theta. So again, we have some formulas for this on the previous page. So if we're converting from rectangular to polar, r is going to be the square root of x squared plus y squared. That is just because r will be the hypotenuse. So we're essentially using the Pythagorean theorem. That would allow us to find r. And then to find theta, I could really use the inverse, any inverse trig function that I wanted to, but you're typically going to have the x and y, which are the opposite and the adjacent, which is why inverse tangent is a great fit for that. Okay, so let's take a look at this one. And again, a sketch might be helpful as you're looking at this. That might also help you kind of verify that you're getting the right coordinates. So if I'm thinking of 1 and negative root 3 is a little bit past negative 1, like negative 1.7-ish. We're here. So wherever my answer is, I want to make sure my answer is also going to land me in that fourth quadrant right here. And if I kind of enlarge this triangle, essentially what I have, maybe I'll make that a little bit bigger. The x coordinate is 1, the y coordinate is negative root 3. So if I want to find out what r is, I'm finding basically the hypotenuse here, or I could think of that if I'm thinking of this in similarity to a vector. It's like finding the magnitude, very similar, just different language here. But I'm going to do the square root of 1 squared plus the square root of negative 3 squared, and I get the square root of 4, which is 2. Now this will always be a positive. We're always taking the principal square root. This formula will give you the positive radius. You certainly could write this in a different representation with a negative radius if you wanted to, but this will give you the positive radius. And then to find out what theta is, I know that the tangent of theta, if theta is right here, the tangent of theta would be in that triangle right there, would be the the y over the x. So y over x. So basically, I'm trying to figure out, well, what angle gives me that tangent in the fourth quadrant? What angle in the fourth quadrant would give me this tangent? Now, most of the time we have like a domain restriction from tangent from negative pi over 2 to pi over 2. But when I'm using polar coordinates, it is helpful to find the actual angle in a positive angle. That's just the most common way. If you write it in a negative angle, that would still be considered correct. But basically what's happening here is I wanted to try to write this in a way that maybe I could identify where these are at. And so really this would be like negative root 3 over 2 over 1/2, and just like the 2's on the denominator would have canceled out. So what I'm looking for is I need an angle where the sine or the y value would have been negative root 3 over 2 and the cosine would have been 1/2. Well, that happens with my pi over 3 angle. So I could represent this as negative pi over 3. That would be fine. I could also represent this if I'm going around clockwise, which is the more common way to represent this with a positive angle clockwise, would be 5 pi over 3 for that angle. Both of them are technically correct, but usually you're going to see this written with the positive angle and measuring counterclockwise this way. All right. So on this next one, we're going to write this again as polar coordinates this time. And so where my angle is, and really if you think about this one, sometimes when these are right on the axes, you could figure this out without actually having to do a lot of work. Like, let's just think about where this one is. If we're writing this in the form of r and theta, this is a radius of 4. And theta, if I think about measuring from the polar axis, is 3 pi over 2. So usually if they're on the axes, you can save yourself some work and just think about, where is that? What is that angle in that position? And how far in the positive direction? However, we could actually use the formula if we wanted to. So r is the square root of x squared plus the square root of y squared. I get the square root of 16. We're always looking for the positive or the principal square root here. And then theta is the inverse tangent of y over x. Well, that's undefined, right? Where do we have an undefined tangent? Well, the inverse tangent is undefined whenever cosine is 0, because it's sine over cosine. So we would have that 0 on the denominator. So we would be either looking at here or here. This is where the picture is helpful. We know that we're down on this negative side of the y-axis. So this would have to be at 3 pi over 2. All right, on to the next page. So we can use those same ideas even if we're converting equations, not just converting coordinates. So those same formulas still work. If we're going from rectangular to polar, or if we're going from polar to rectangular, we have these relationships that are true that we can refer back to. X is equal to r times the cosine of theta. Y is equal to r times the sine of theta. R is equal to the square root of x squared plus y squared, and theta is the inverse tangent of y over x. All of these things are true, and we can use them whenever it is convenient. If we think about what we're trying to do, that'll help us know where we should start. These ones, we're starting off with things that are x's and y's, and we want them to look like r's. And so anytime you see an x, you could replace it with r cosine theta, which is super helpful. In fact, that's what I'm going to do down here. I'm going to say 3x would be 3r cosine theta minus r sine of theta, I'm just replacing y, is equal to 6. Now what we want is we want a polar equation, which we've not really talked about. What is a polar equation? We're going to really spend more time on this the rest of this lesson and the next couple lessons. It says expresses r in terms of theta. So what they'll look like is they'll look like r equals something, and then we'll have theta in as part of the answer typically. So it is possible to just have r equals a number. That's less common, but that could happen. But r needs to be isolated, and that's what that yellow part means. So since r needs to be isolated, I now have r on the left-hand side of number 9, but I have it in two expressions. I'm going to factor r out as the GCF. And then to isolate r, I will divide. R is equal to 6 over 3 times the cosine of theta minus sine of theta. Now, right now, that might just feel like mumbo jumbo to you a little bit, but this is actually our solution. This is our answer. And you have no experience at this point in time on knowing what does this equation even mean? What does this do? That's okay. But that is still done the requirement. We've converted this. We don't have x's and y's anymore. We have only r's and thetas, and r is isolated. And that's what we're trying to do. Just a quick note. This 6 and this 3 do not divide out. Why? The reason why is because 3 is not a factor of the entire denominator. 3 is only a factor of cosine. It is not a factor of sine. So I could only reduce out or divide out a factor of 3 if that 3 is a factor of the entire denominator, which it's not. One way to stop yourself from reducing things that you shouldn't is to always ask, is there a GCF that I can factor out? If there's no GCF, there's nothing to reduce. So just kind of FYI, if you start by factoring before you reduce, it'll save you from making some algebraic errors that can cause you frustration. All right, let's take a look at this next one. We have x squared, and x can be replaced with r cosine theta. When I square that, I want to square both the r and the cosine. This is how we'll show squaring cosine, like this. It's kind of like when we've got like logs and things like that, how we could put that power right there. Okay, and then this next part, we have y plus 1, and then that's being squared. Now, I'm going to be a little more careful here because this is a binomial. So y is r sine of theta, and then that's plus 1. And then all of this is equal to 1. Well, when I square that, I do need to be careful to properly expand this. You can think of FOIL. You can think of the distributive property. Lots of different ways that people think about that, but just be careful here to make sure you expand that out as a binomial times a binomial. Here's what we end up with. We'll have r cosine squared of theta plus r sine theta times itself. That'd be r squared sine squared theta. And then we'll have r sine theta times 1. And then we'll have that same thing again. So we'll have twice r sine theta, because I have that same term twice, plus 1, and then that equals 1. So what does this mean? Now remember, our goal is to write an equation that looks like r equals something. R equals something. So any term that does not have an r, I'm going to move over to the opposite side. In this case, when I subtract 1 from both sides, it'll zero out. That doesn't happen in every single situation, but it will happen here. I also have something interesting that's happening with the cosine squared plus sine squared. You might remember this from previous units. In chapter 4, we talked about this. This is the Pythagorean identity. Cosine squared of theta plus sine squared of theta is equal to 1. Now these both have a multiplier, but what I'm going to do is for just these two terms, I'm going to factor out, oops, I have a little handwritten typo. Let me fix that. I'm going to factor out the GCF of those two terms, which is r squared, times the cosine squared of theta plus the sine squared of theta. And then I have plus 2r sine of theta. And then that equals 0 when I move the positive 1 over to the other side. Cosine squared of theta plus sine squared of theta is 1. So this is really r squared plus 2r sine of theta equals 0. It's starting to look less complicated. My goal is to get r alone, so I'm going to factor a GCF out. I have r times r plus 2 sine of theta. And then this is interesting. If we use the zero product property, each of these could be set equal to 0. R is equal to 0, or r plus 2 sine of theta could be equal to 0. Well, what does this mean? If r is equal to 0, r is the length that we are away from the origin. If we're 0 units away from the origin, that's just this point that's at the origin. That's all that is. And sometimes people call that also the pole right here. This point right here, often in polar coordinates, we'll call that the pole right there. And that's not actually what we're looking for in our answer. Okay, that is a point. That's a useful place where this is equal to 0, where r is equal to 0. It's true, but it's not actually what we're looking for. What we're looking for is an equation here, not just where r is equal to 0. So we're not going to really worry about that. We're going to really focus on this part. And so r then, if I isolate it, is equal to negative 2 sine of theta. This right here, again, was just a point. All right, now we're going to go the opposite direction. We're going to start with polar equations. We're going to work backwards to make rectangular equations. So we would like x's and y's to be in the equation. So I'm going to be using these formulas so that I can, if I start with r, I can introduce x's and y's. If I start with theta, I can introduce x's and y's. So let's just start with this first one. Where r is, I will replace that, substitute in that with the square root of x squared plus y squared equals 4. You might not quite recognize that, but if I then square both sides, I would end up with x squared plus y squared is equal to 16. Well, that's interesting. That's a shape that you probably recognize. That is a circle centered at the origin with a radius of, my gosh, my scale is so off, but let's try this again. That's like a radius of 4. This is a circle with a radius of 4. In fact, let's think about this. The equation r equals 4 means we want all points that have a radius of 4. All points that are 4 units away from the origin or from the pole. Well, that would be a circle. These are all the units that are 4 units away from the origin. All right, let's take a look at this next one. This time we have theta. And so what we want to do is we want to be able to use this. Now, this equation could be written differently. We could, if we didn't want to use an inverse trig function, we could write this one as the tangent of theta is y over x. So that might actually be more useful if I'm taking a look at this one, because what I can do is I can write both sides. I can take the tangent of both sides. You may not have even known that you could do that, but this is part of our equivalent balancing that we're allowed to do in an equation from algebra. So we're going to take the tangent of both sides on here to get this look more familiar. So I'll have the tangent of theta is equal to the tangent of 3 pi over 4. Well, the tangent of theta would be y over x, and the tangent of 3 pi over 4 is here. We know that 3 pi over 4 is negative root 2 over 2 So the x and the y's are the same, but with different signs, so that would equal negative 1. And it's most common when we have a linear function, which degree run for both terms would mean linear. If we get y isolated, this is the most common way to write that answer. Technically, this answer is also correct. Kind of an interesting strategy, though. If we have that theta and I don't have anything else with it, I could write tangent in there on both sides so that I could then do some substitution. All right, let's take a look at this one. This one's actually a really interesting idea for a strategy. Looking at this one, I have r is equal to -2 times the secant of theta. Well, what is the secant? Maybe let's put this into something that's more familiar. This is r is equal to -2 over the cosine of theta. And we could replace r with the square root of x squared plus y squared, but it ends up kind of becoming complicated because I've got that cosine. However, you might remember that r times the cosine of theta is x. So if I see that cosine in there, what I could do is cross multiply here. And I have r cosine of theta is equal to -2, and r cosine of theta is x. This is, surprisingly enough, this is the vertical line, like right here, x equals -2. That's what this is, which is a really weird thing. It's actually like surprising, but lines, most polar equations will form these graphs with curves, lots of like circular shapes and curves, but you can have lines in there and straight edges, which is interesting to think about. All right, let's take a look at this one. And so on this one, what I could do is I see that sign. And what I'd really love is my goal is to try to have like an r sine of theta, because then I could replace that with y. So I remember when I was first looking at this, I was like, could I divide both sides by sine? That gives me r divided by sine theta, not what I'm looking for. Or could I divide both sides by r, which is kind of scary to do. Sometimes when you divide by a variable, you lose a solution. But okay, maybe I could do that. But again, then I'd get sine of theta over r. What I want is sine of theta times r. So kind of like what we did in number 12, where I took the tangent of both sides. This time what I'm going to do is I'm going to multiply both sides by r. That's helpful because then I get something. I'll just sneak the r in here by the commutative property of multiplication. 10r is the same as r10. Usually write the 10 in the front. But r sine of theta, remember, is really y. Now I still have r squared over here. Well, r squared, remember that r is the square root of x squared plus y squared. So then r squared, if I square both sides, would be x squared plus y squared. Technically, this has met the requirements of the directions. However, I think that there's a lot of times that on your homework, you might be asked to write this in a different form. Maybe to write this in a form of a conic. I don't know if you recognize this, but this is the equation of a circle. It's an equation of a circle, though, where it's not easy to see where the vertex is. So I want to show you how you can convert this. We will talk about this more when we get to chapter 9 and we review conic sections. But what I can do is I can rewrite this as x squared plus y squared minus 10y is equal to 0. I'll just group all of my variable terms together. X squared is a perfect square. I'm going to leave that alone. But for y squared, what I want to do is I want to add something. And whatever I add to this side, I will also add to the other side of the equation. I really have a 0 here right now. So that my equation is balanced. And I just want to be strategic about what I add. I'm going to complete the square. So what I'm going to add is I'm going to take the value of b, divide it by 2, and square it. And I will balance the equations by adding that to both sides. What I've done when I do this is I've created a perfect square trinomial for the y terms that can be factored out as a binomial times itself. The two factors of 25 that add to -10 are -5 and -5. They're actually those numbers right there. So this would be y minus 5 times y minus 5 quantity squared. And here is my equation of a circle. We could just see the vertex of, or the center of the circle a little easier this way at 0, 5. Radius is 5, which is kind of interesting. All right, the last part of our notes for today is going to have us just look at a couple of these equations so that we can start to see some relationships. First of all, for circles, if they are centered at the origin, In rectangular form, we're used to seeing them x squared plus y squared equals r squared. Again, these are ones centered at the origin. In polar form, if they're centered at the origin, we would just have r equals a number, like r equals 5, r equals 10, whatever, however long the radius is. In fact, looking below, we have that a couple times. Number 15 and number 18 are going to be circles. We have a situation where we need to always be 3 units away from the origin. Well, that would be, wow, that is the best circle I've ever drawn. You don't realize how bad your circles are until you have to trace. That's my circle. The radius is 3. Number 18, same form. This one, the circle's 5, has a radius of 5. And slightly better, r is 5. Right on there. Okay, so the other thing we could have is we might have some lines, and a common way for these lines to look, if they are not horizontal or vertical, is we're going to have ones that pass through the origin. We would have y equals mx plus b, but the b value is 0 if it goes through the origin. When we're looking at a polar form for an equation of a line, you're going to see 2 different ways. We might see theta is equal to the inverse tangent of some value. Or we might see theta equals k. K would just be the angle that we would have found from the inverse tangent of some measurement. And so a lot of the ones we're going to be looking at will be this way. So it's just basically a line that goes through a certain angle. So here's what that would look like. If I think about where's pi over 4, pi over 4 is like right here. So theta equals pi over 4 would mean that we are going through that angle, and it doesn't matter what radius we use. In fact, we could even use a negative radius. So since we could use all radii, r is not even in the equation, it would look like that. This is the line theta equals pi over 4. All radii would be included there. If I look at theta equals 2 pi over 3, that would be the line that goes through the position 2 pi over 3. Well, 2 pi over 3 is right here as the position, but I would want to use all radii along that angle position, including negative radii, so it would go back in both directions. This is theta equals 2 pi over 3. Super important, next class, you are going to need a laptop. So please bring your laptop. It could be the school-issued laptop or it could be your own, but you are going to need it. It is super important, so please make sure you bring that next class. That is the end of this video.